Time warps dramatically across the cosmos, bending to the will of gravity and speed. This is not a fantasy, but the core of Einstein's theory of relativity, a reality that shatters our everyday understanding of time. In this exploration of when time slows down, you will gain a completely new way of seeing the universe, from the smallest particle to the grandest galaxy. How can a clock on a satellite run at a different speed than one in your hand? What happens to time at the edge of a black hole, where gravity becomes infinite? We will uncover the science behind these cosmic mysteries and reveal how this hidden force of time dilation shapes everything we see. By the end, your perception of reality will be fundamentally altered. What does it truly mean for time to be relative? For centuries, the steady tick of a clock seemed to be the one thing everyone could agree on. It was a universal heartbeat, an absolute river flowing at the same rate for everyone and everything, from a falling apple to a distant star. This was the comforting worldview established by Isaac Newton, a framework so intuitive it felt like common sense. But this universal time was an illusion, a grand and deeply held assumption that would be completely overturned. The dismantling began not in a grand university, but in a quiet patent office where a young clerk named Albert Einstein was dreaming about the nature of light and motion. His theory of relativity introduced a concept so radical it seemed to defy logic itself. Time is not a constant. It is a fluid, personal experience woven into the very fabric of space. Your passage through time is intimately tied to your own journey, to how fast you are moving and the strength of the gravity you are feeling. This means the idea of a single, universal now is a mirage. Imagine two flashes of light, one at the front and one at the back of a moving train. For a passenger sitting perfectly in the middle, these flashes appear to happen at the exact same instant. They are simultaneous, but for another person standing on the platform as the train rushes by, the story is completely different. From that outside perspective, the flash at the front of the train actually happens first. The same two events, judged differently based purely on the observer's state of motion. There is no privileged clock in the universe. Your now is not necessarily my now. This profound shift in thinking from a single universal time to a personal and relative one is the essential first step to unlocking the greater cosmic mystery. It prepares us to ask the next, even more startling question. If time is not absolute, then how and where does it actually bend? This strange slowing of time reveals itself most clearly when we push the limits of speed. Einstein's special theory of relativity gives us a powerful lens to see this, transforming a simple story about twins into a cosmic revelation. Think of two siblings completely identical. One chooses a quiet life on Earth, while the other boards a spacecraft capable of flying at an incredible pace, a substantial fraction of the speed of light. After a long journey, the spacecraft returns home. As the hatch opens, the family expects a joyful reunion of equals. Instead, they are met with a silent, profound shock. The astronaut sibling steps out, looking noticeably younger than the twin who never left the ground. The traveler has experienced less time. This is the famous twin paradox, a real effect predicted by the laws of physics. The principle is both simple and astounding. The faster you move through space, the slower your own personal clock ticks relative to someone who is standing still. Your high velocity literally stretches out the seconds, minutes, and years from the perspective of a stationary observer. This is not a mechanical error or an illusion. It is a fundamental property of the universe, described by a set of mathematical relationships known as the Lorentz transformations. These equations show us exactly how time dilates and lengths contract as an object's velocity increases. The effects are tiny at everyday speeds, but they become immense as you approach the cosmic speed limit of light itself. This is not just theoretical. The satellites that power the GPS in your phone are constantly proving Einstein right. They orbit the Earth at thousands of miles per hour, and their incredible speed causes their onboard atomic clocks to fall behind clocks on the ground by a tiny amount every day. If engineers did not deliberately correct for this relativistic slowing, the entire system would become useless within hours, misplacing your location by several miles. So speed is far more than just covering distance. It is a direct trade with time itself, a currency that buys you a different experience of reality. And if velocity can warp time so dramatically, what happens when we introduce the universe's other great force? Gravity itself now enters the stage, not as a simple force, but as the master architect of spacetime. Einstein's general theory of relativity completely reimagined this most familiar of pulls. It revealed that massive objects like stars and planets do not exert a force across a distance. Instead, they create a depression in the fabric of the cosmos, much like a heavy ball placed on a stretched rubber sheet. This curvature is what we experience as gravity. An object simply follows the most direct path through this warped landscape, a natural curve we perceive as falling or orbiting. And just as a ball would roll faster down a steep slope, time itself flows at different rates depending on where you are in this gravitational terrain. The stronger the gravity, the deeper the warp, and the more profoundly time slows down. Picture two identical, incredibly precise clocks. One is placed at the bottom of a deep valley at sea level, and the other is carried to the summit of a towering mountain. Though they are separated only by vertical distance, they will gradually fall out of sync. The clock bathed in the stronger gravity at sea level will tick just a little slower than its counterpart high in the thinner air. The difference is minuscule, but it is undeniably real, measured repeatedly with atomic clocks. This gravitational time dilation is not confined to our planet. It is a universal rule. The light struggling to escape the intense gravity of a distant star loses energy, its waves stretching out and shifting toward the red end of the spectrum. This phenomenon, called gravitational redshift, is the direct signature of time itself slowing down in a powerful gravitational field. So while speed is one way to trade for time, gravity is the other, more pervasive currency. It means that your head is literally aging faster than your feet by a tiny, almost imperceptible fraction. And if this is true for a planet, what must it be like at the edge of the most gravitationally dominant objects in the known universe? To truly grasp these cosmic rules, we need to understand how Einstein himself first saw them. He did not have advanced laboratories or space telescopes. His primary tool was pure, unadulterated thought. He constructed entire universes in his mind, using simple, elegant scenarios to tease apart the fabric of reality. One of the most powerful of these is the light clock. Imagine a clock built from nothing but two parallel mirrors and a single particle of light, a photon, bouncing perfectly between them. Each round trip from the bottom mirror to the top and back again counts as one tick of this clock. Now picture this clock at rest. The photon's path is a straight, vertical line. It is the shortest possible distance, but what happens when the clock is set in motion, moving sideways at a tremendous speed? From your perspective as a stationary observer, the story changes completely. As the clock moves, the photon must now chase the moving mirror. Its path is no longer a simple up and down line. It has become a longer diagonal zigzag. Since the speed of light is an unbreakable cosmic constant, the only way for the photon to cover this longer diagonal distance in the same time is for each tick of the moving clock to take longer from your point of view. Time itself on the moving clock has slowed down. This simple mental model, built from a few basic principles, reveals the unavoidable truth of time dilation. It is a consequence of light's fixed speed and the geometry of motion. Einstein then took this powerful way of thinking a step further with another famous thought experiment. Imagine you are in a sealed, windowless room, floating in the depths of space, far from any planet or star. If this room begins to accelerate at a constant rate, you would feel your feet pressed firmly against the floor, just as if you were standing in Earth's gravity. If you dropped an object, it would appear to fall. There would be no experiment you could perform inside that box to tell whether you were in a rocket accelerating through empty space or simply sitting at rest in a gravitational field on Earth. This profound equivalence between acceleration and gravity became the cornerstone of his general theory of relativity. It suggested that gravity is not a mysterious force reaching across space, but a feature of the geometry of spacetime itself. These thought experiments were not just playful daydreams. They were the rigorous intellectual tools that allowed a single human mind to decode the operating manual of the universe, leading directly to the complex mathematics that describes everything from orbiting planets to the bending of starlight. These elegant mathematical relationships transform our mind-bending concepts into precise, testable predictions. At the heart of special relativity lies a deceptively simple formula known as the Lorentz factor. Represented by the Greek letter gamma, this factor calculates exactly how much time stretches for an object as its velocity increases. The equation itself is straightforward. Gamma equals 1 divided by the square root of 1 minus the ratio of your velocity squared to the speed of light squared. At everyday speeds, like driving a car or even flying a jet, this ratio is nearly 0, making gamma almost exactly 1. Time proceeds normally, but as your speed climbs to a significant fraction of light speed, that ratio grows and the denominator of the equation shrinks, causing the value of gamma to balloon. At 87% of light speed, gamma is 2. For the astronaut twin traveling at this velocity, every single tick of their clock would take 2 seconds from the perspective of Earth. They would age only half as fast. This single mathematical term perfectly captures the trade-off between speed and time. General relativity, however, demands a more complex language to describe how mass and energy shape the cosmos. This language is written in the form of metric tensors and the Einstein field equations. These are not simple formulas but intricate sets of equations that define the geometry of spacetime itself. They tell us how the presence of a massive object like a star warps the space and time around it, creating the curves that guide planets and slow clocks. We do not need to solve these advanced equations to grasp their meaning. We can look at one of their most famous solutions, the Schwarzschild metric, which describes the spacetime around a simple, non-rotating black hole. This metric reveals a profound relationship. The closer you get to such an object, the more time slows down relative to a distant observer, approaching a full stop at the event horizon. The key variable is the gravitational term, 1 minus 2 times the gravitational constant times the mass, divided by the speed of light squared times the distance. This term dictates the flow of time. Far from the black hole, the term is nearly 1 and time flows normally. But as you approach the event horizon, the denominator grows and this term approaches 0, meaning time for you from the outside perspective grinds to a halt. This mathematical skeleton is not abstract speculation. It is the very framework that allows engineers to correct GPS satellite clocks and enables astronomers to predict the precise orbit of Mercury. The numbers are not just symbols on a page. They are the hidden code of the cosmos, verified with astonishing accuracy and pointing toward even deeper mysteries at the edge of our understanding. Out in the deep void, nature has built its own perfect laboratories for testing relativity. These are neutron stars, the collapsed cores of once massive suns. When a giant star ends its life in a supernova explosion, the outer layers are blasted into space, but the core collapses under its own immense weight. The result is an object of almost unimaginable density. A single teaspoon of neutron star material would weigh billions of tons, as much as a mountain. This incredible mass, squeezed into a sphere no wider than a city, creates a gravitational field so powerful it warps the spacetime around it to an extreme degree. But some of these stellar remnants offer an even clearer signal. They spin. A pulsar is a rapidly rotating neutron star that beams radiation from its magnetic poles, much like a cosmic lighthouse. If this beam sweeps across Earth's line of sight, we detect a perfectly timed pulse of radio waves with every rotation. Some pulsars spin hundreds of times per second, and their rhythm is more precise than any atomic clock we can build. This unwavering regularity is what makes them so valuable. Astronomers can detect fantastically small deviations in their ticking. They have observed that the pulses from a pulsar locked in a tight orbit with another dense star arrive at Earth slightly delayed when the pulsar swings through the stronger gravity of its companion. This is a direct measurement of gravitational time dilation, a real-world confirmation that time itself is slowing down in that deep gravitational well. Furthermore, the precise timing reveals another subtle effect predicted by Einstein, the dragging of spacetime. As a massive object spins, it literally twists the fabric of the cosmos around it, a phenomenon known as frame dragging. The orbit of a pulsar can be minutely altered by this spacetime whirlpool, and the changes are written in the timing of its pulses. These cosmic clocks do not just tell us the time. They tell us about the very nature of space and time, demonstrating that the universe operates according to the rules of relativity in its most extreme environments. If neutron stars warp the fabric of time, black holes take that thread and snap it. This is the ultimate expression of gravity's power, a place where the rules of relativity are pushed to their absolute limit. The event horizon of a black hole is not a physical surface you could touch. It is a mathematical boundary, the point of no return where the escape velocity equals the speed of light itself. Beyond this threshold, not even light can fight its way out. It is here that gravitational time dilation achieves its most extreme and paradoxical form. From your safe vantage point, watching a spacecraft fall toward this abyss, you would witness something profoundly strange. The ship's clock would appear to tick slower and slower and slower still. As it nears the event horizon, its signal would stretch into an infinite, agonizing crawl. The light from its hull would redshift dramatically, draining of energy and shifting from visible light to infrared, then to radio waves before finally fading into nothingness. From your perspective, the falling object never actually crosses the line. It simply smears across the surface of the horizon, a frozen fossil etched in spacetime for the rest of time. Yet for the astronaut inside that vessel, the experience is terrifyingly different. Their own wristwatch would continue its steady, normal ticking. They would feel no special sensation as they passed the event horizon, crossing a boundary they could not see. But the view out the window would be utterly transformative. Looking back toward the universe they left behind, the incoming light from stars and galaxies would be blue-shifted and compressed, accelerating into a blinding, concentrated ring of light. The entire future history of the cosmos, billions of years of cosmic evolution, could flash before their eyes in a finite and tragically short amount of their own personal time. This stark contradiction is not a flaw in the theory. It is the ultimate lesson in relativity. There is no single, universal experience of time. Your reality is defined by your path through the warped geometry of the cosmos. For the outside observer, time at the horizon has stopped completely. For the one falling in, time proceeds, but the fate of the entire external universe is pulled into their final moments. This is gravity's final, absolute dominion over the clock, a demonstration that in the deepest wells of spacetime, time itself can lose all meaning. The same cosmic rule that freezes time at a black hole's edge is quietly at work in our own solar system. Even our familiar sun, the anchor of our planetary family, creates a gentle slope in spacetime that alters the flow of time itself. A clock placed on the sun's searing surface would tick more slowly than an identical clock floating in the distant void between planets. This is not a hypothetical idea. It is a continuous, subtle gradient of time that stretches from the heart of our star out to the frozen orbits of the outer planets. Each world exists in its own distinct time frame, dictated by its position within the sun's gravitational well. Mercury, orbiting close to the solar furnace, experiences a slightly slower passage of time than the gas giant Jupiter, which basks in a much weaker region of the curvature. The difference for any single second is infinitesimal, completely undetectable to our human senses. Yet for the robotic explorers we send across the solar system, this tiny effect is absolutely critical. A spacecraft navigating the vast distance to Mars does not simply move through empty space. It travels through a landscape where time itself flows at subtly different rates. The ultra-precise atomic clocks used for navigation must account for this relativistic warping. If engineers did not deliberately adjust for the time dilation between Earth and the spacecraft's position, the cumulative error would throw its trajectory off by miles. Our very ability to land a rover on another world depends on recognizing that time is not a universal constant, but a local experience shaped by the gravity of every star and planet we pass. Every time you use your phone to navigate, you are conducting a silent experiment in relativity. The global positioning system is a constellation of satellites, each one a flying clock hurtling through space. These are not ordinary timepieces. They are atomic clocks of such incredible precision that they would not gain or lose a second in over 1,000,000 years. Yet, according to Einstein's theories, they are constantly falling out of sync with the clocks on Earth. This is not a malfunction. It is the universe operating exactly as predicted. The satellites move at tremendous speeds, about 14,000 kilometers per hour. This velocity alone, as special relativity dictates, causes their onboard clocks to tick slower than stationary clocks on the ground. The math is precise. They lose roughly 7 microseconds each day. But then, general relativity adds its own profound twist. Orbiting high above the Earth, these satellites experience a slightly weaker gravitational pull. In this shallower well of spacetime, time actually speeds up. Their clocks gain about 45 microseconds every single day. These two effects do not cancel each other out. They combine. The gravitational effect is stronger, resulting in a net gain of 38 microseconds daily. This number seems almost invisibly small to us. But for the hyper-precise calculations of triangulating your position, it is an enormous error. Without a deliberate, programmed correction for this relativistic drift, the entire system would unravel. The timing signals from the satellites would be just slightly wrong. Your calculated location on Earth would drift by several kilometers each day, making turn-by-turn navigation completely impossible within hours. So engineers build this correction directly into the system. Before a satellite even transmits its time signal, its clock is artificially adjusted to account for the warping of time. This means your ability to find a coffee shop or follow a map is directly dependent on our understanding of black holes and cosmic time dilation. It is a daily, invisible, and utterly essential proof that Einstein's vision of a flexible, relative universe is not just a theory. It is the hidden framework that makes our modern world work. This same curvature that slows time also guides the very path of light. When a distant galaxy's light travels toward us, it does not always fly in a perfectly straight line. If its journey takes it near a massive galaxy cluster, the profound warp in spacetime created by that cluster acts like a vast cosmic lens. The light is forced to follow the curves of this warped geometry, bending around the massive object in its path. This phenomenon is gravitational lensing, a stunning visual confirmation of Einstein's universe. The light is not being pulled by a force. Instead, it is simply following the most direct route through a landscape where space and time are already bent. This path is known as a geodesic, the natural trajectory through curved spacetime. It is the very same path of maximum time dilation, where the flow of time is most significantly altered. The results are breathtaking. We do not see a single, clear image of the background galaxy. Instead, the intervening cluster can smudge that galaxy into long, luminous arcs. It can split the image into multiple, identical copies arranged around the lens. In a perfect alignment, the light forms a complete halo around the foreground mass, a shimmering circle in the void known as an Einstein ring. This is more than just a beautiful cosmic illusion. It is a powerful tool. Gravitational lensing acts as a natural telescope, magnifying the light from galaxies so ancient and faint they would otherwise be invisible to our instruments. It allows us to peer deeper into the cosmic past than ever before, but it also serves a deeper purpose. The precise shape and distortion of that background light provides a direct map. It charts the invisible gravitational field of the lensing cluster, revealing not only the distribution of its visible stars but also the haunting presence of its dark matter. In mapping this gravity, we are also mapping the temporal terrain of the cosmos, seeing directly where time itself is being stretched and slowed. The bending of light and the slowing of time are two sides of the same coin, both born from the elegant curvature of spacetime. The stretching of space itself adds another profound layer to time's relativity. Across the vast intergalactic voids, the very fabric of the cosmos is expanding, carrying galaxies away from one another like raisins in a rising loaf of bread. This grand motion leaves a distinct fingerprint on the light traveling toward us. As a distant galaxy recedes, the space through which its light journeys is continuously stretching. This stretches the light waves themselves, shifting them toward the red end of the spectrum. This cosmological redshift is more than a color change. It is a direct signal of a cosmic clock running at a different rate. The decreasing frequency of that ancient light can be interpreted as a form of time dilation for the entire emitting galaxy. From our perspective here and now, the clocks in that far-off island universe appear to be ticking slower. When we point our most powerful telescopes at the earliest, most distant quasars, we are effectively looking back over 13 billion years. We are not just seeing them as they were in their youth. We are witnessing a universe where the fundamental rhythm of time was different. The combined effects of the universe's rapid early expansion and the incredible velocity of these receding objects means their light arrives in a profoundly stretched and time-dilated state. Their frenetic variability, which might have flashed over days in their own time frame, appears to us as a slow, majestic drift over many years. This connects the largest scale structure of reality, the expanding cosmos, directly to the most personal experience of time. The history of the universe is not just written in the positions of galaxies, but in the relative ticking of clocks separated by billions of light years. It suggests that the flow of time is woven into the expansion of space, a single, unfolding phenomenon that defines the past, present, and future of everything we see. In September 2015, a subtle tremor was felt in the cosmos. The twin detectors of the LIGO Observatory, separated by thousands of kilometers, registered an almost imperceptible signal. After decades of searching, scientists had made the first direct detection of gravitational waves. These were not waves of water or sound, but ripples in the very fabric of spacetime itself, generated over 1 billion years ago by the final, violent dance of two black holes spiraling into one another. As these waves radiated outward at the speed of light, they carried with them a propagating distortion of gravity. Picture a calm pond suddenly disturbed by a falling stone. The ripples expand, causing the water's surface to rise and fall in a rhythmic pattern. Gravitational waves do the same to the three-dimensional stage of space and time. As a wave passes through an object, it literally stretches space in one direction while simultaneously compressing it in the perpendicular direction. This stretching and squeezing applies not just to physical objects, but to the dimension of time itself. The flow of time in a region of space oscillates, speeding up and slowing down in a delicate, rhythmic dance with the warping of space. This effect is incredibly tiny, far too small for humans to perceive, but the LIGO instruments are designed to measure it. They use lasers traveling down 4-kilometer-long vacuum tunnels to detect a change in length thousands of times smaller than a single proton. The successful detection was far more than a simple checkmark for Einstein's theory. It was humanity's first direct measurement of dynamic spacetime. We were no longer just observing the static warps created by massive objects. We were feeling the cosmos vibrate, listening to the echoes of the most energetic events in the universe. This opened an entirely new sense for exploring reality. Where traditional astronomy sees the glow of stars, gravitational wave astronomy hears the deep, rhythmic drumbeat of colliding black holes and neutron stars, a symphony played on the flexible, dynamic stage where time itself unfolds. Even our search for new worlds is guided by the silent hand of relativity. The most successful planet hunting technique, the Doppler method, relies on a simple principle. As a planet orbits its star, its gravity tugs the star back and forth, creating a subtle wobble. We detect this wobble by watching the star's light. As the star moves toward us, its light waves are compressed, shifting slightly toward the blue. As it moves away, the light stretches, shifting toward the red. But this stellar dance is not happening on a flat, static stage. The light carrying this signal is itself climbing out of the star's gravitational well, a journey that relativistically redshifts its color. To accurately measure the true wobble and calculate the planet's mass, astronomers must first subtract this gravitational redshift from the observed signal. It is a tiny correction, but a vital one, ensuring we are not misled by the warping of spacetime around the star itself. Another clue emerges from the precise timing of planetary transits, the moment a distant world crosses the face of its star. Sometimes the transit occurs a fraction of a second earlier or later than predicted. This transit timing variation can be a sign of another, unseen planet gravitationally nudging the first. Yet this delicate clock can also be skewed by relativity. The light from that star system carrying the signal of the transit does not travel through empty space. Its path may be curved by the gravity of intervening galaxies or dark matter halos, subtly altering its travel time to our telescopes. We are not just seeing a delay. We are witnessing the accumulated effect of time flowing at different rates along the light's billion-year journey. For the most extreme planetary systems, the effects become even more profound. Imagine a world orbiting a neutron star, a place where the parent star's gravity is so intense that time on its surface slows to a crawl relative to the universe outside. This gravitational time dilation could, in theory, leave a faint imprint on the planet's observed orbital period, making its year appear just slightly longer from our distant vantage point than it would for an observer right next to the system. These are not mere curiosities. They are essential reminders that we cannot fully understand an alien world without first understanding the flexible, dynamic spacetime it calls home. But all these relativistic effects present a profound puzzle. Time can slow down and speed up, yet it always seems to flow in one irreversible direction, from the settled past into the open future. Why does time have an arrow? The answer lies not in the warping of space-time, but in a fundamental cosmic tendency toward disorder, a principle known as the second law of thermodynamics. This law states that the total disorder or entropy of an isolated system always increases over time. It is the reason a shattered glass does not spontaneously reassemble itself, and why heat always flows from a hotter object to a colder one. The entire universe is the ultimate isolated system, and its entropy is constantly rising. This gives us a thermodynamic arrow of time, a clear direction from order to disorder. To understand where this arrow comes from, we must look back to the very beginning. The early universe, moments after the Big Bang, was in a state of extraordinarily low entropy. It was an incredibly hot, dense, and uniform soup of energy, a state of profound order. As the cosmos expanded and cooled, this orderly state began to unravel. Matter clumped into galaxies, stars ignited, and complex structures emerged, all while the overall disorder of the universe relentlessly increased. This cosmological expansion and the initial low entropy condition are what set the arrow of time in motion. The relativistic warping of spacetime we have explored is deeply intertwined with this process. The specific distribution of matter and energy from the Big Bang created the gravitational hills and valleys that slow time, and that same distribution provided the initial conditions for entropy to begin its long, irreversible climb. This suggests a breathtaking possibility. The flow of time we experience so personally, the relentless march from past to future, may not be a fundamental feature of reality at its smallest scales. Instead, it could be an emergent property, a large-scale consequence of the universe's structure and its ongoing journey from a state of low entropy to high entropy. Our perception of time's flow is woven from the very fabric of cosmic history. Yet this elegant cosmic clockwork faces a profound challenge at the very edges of our understanding. The universe operates under two magnificent but conflicting sets of rules. On the grand stage of stars and galaxies, Einstein's general relativity reigns supreme, describing gravity as the smooth curvature of spacetime. But zoom into the microscopic world of atoms and particles, and you find the bizarre and probabilistic laws of quantum mechanics. Both theories are spectacularly successful in their own domains, but they speak entirely different languages about how reality works. When and where do these two fundamental descriptions of our universe collide? The answer lies in the most extreme environments imaginable, at the very center of a black hole, or at the moment of the Big Bang itself. Gravity becomes so unimaginably strong and is confined to such a tiny point that both theories are essential. Yet when we try to apply them together, they produce nonsensical answers like a calculator that flashes an error message. The smooth fabric of spacetime described by relativity seems to shatter into a chaotic, frothing sea of probabilities at the quantum scale. This is the great unsolved problem of quantum gravity, the search for a single theory that can describe the force of gravity under the rules of the quantum world. In this quantum gravitational soup, our comfortable idea of time begins to unravel. We have seen how time slows down and speeds up, but what if time itself is not a fundamental ingredient of the universe? Some of the most promising theories, like loop quantum gravity or string theory, suggest a startling possibility. They propose that what we experience as the continuous flow of time may actually emerge from something deeper and more basic, a timeless quantum state of interconnected relations. Think of the smooth motion of a movie on a screen. It appears continuous, but we know it is actually made of a rapid succession of still frames. In a similar way, our flowing time might be a projection from a more fundamental reality where there is no time at all, only quantum events or vibrating strings. This means that in the heart of a black hole, or at the beginning of everything, the question of when time slows down might become meaningless. Time, as we know it, might simply cease to exist. This is not just a philosophical puzzle. It is the bleeding edge of physics, a mystery that forces us to reconsider the very nature of reality and our place within it. Our journey to understand time's flexibility may ultimately lead us to a realm where time itself is an illusion. These theoretical threads weave into one of relativity's most mind-bending possibilities, the potential for journeys into the past. General relativity, in its pure mathematical form, does not explicitly forbid time travel. Certain specific solutions to Einstein's equations describe pathways known as closed time-like curves. Imagine your personal timeline, the unbroken thread of your existence from birth to this moment, not as a straight line, but as a loop curling back to rejoin itself. An object or person following such a path would eventually return to their own past, creating a scenario where cause and effect could become entangled in a knot. This is not science fiction, but a direct, if highly speculative, interpretation of the geometry allowed by the theory. The cosmos might, in principle, contain structures like infinitely long, rotating cylinders or traversable wormholes, bridges through spacetime that could be configured to form such a loop. Yet the universe seems to guard its chronological order fiercely. The moment you consider the implications, profound logical puzzles emerge. The most famous is the grandfather paradox. If you were to travel back in time and prevent your own grandfather from meeting your grandmother, you would create an impossible contradiction, a reality where you could never have been born to make the journey in the first place. This paradox strikes at the heart of causality, the fundamental principle that cause must always precede effect. It suggests that the seamless flow of time we experience might be a necessary feature to maintain a logically consistent universe. Most physicists believe that nature has a built-in mechanism to prevent these causal violations. The renowned physicist Stephen Hawking proposed the chronology protection conjecture, an idea that the laws of physics, particularly quantum effects, would always intervene to disrupt a closed time-like curve before it could be used. It is as if the universe possesses a kind of immune system against paradox, ensuring that history remains a single, consistent story. While we will almost certainly never build a time machine, the very fact that our best theory of gravity allows us to even pose the question is staggering. It forces us to ask what it truly means for the past to be fixed and the future to be open, challenging our most basic assumptions about free will and destiny. This theoretical exploration reveals that the cosmos may value logical consistency above all else. weaving the arrow of time directly into the fabric of what is possible. Science fiction has long turned these abstract equations into gripping human drama, translating the cosmos's silent rules into stories of love, loss, and impossible choice. Perhaps the most famous example is the film Interstellar, where a crew visits a planet chained to a supermassive black hole. The immense gravity of this cosmic beast warps time so severely that a single hour on the planet's surface passes as 7 long years for their comrades waiting in orbit. This is a dramatic, if artistically heightened, portrayal of gravitational time dilation. The crew's desperate race against the planet's crashing waves becomes a race against time itself, not for their own survival, but against the aging of everyone they left behind. When they return to their ship, they confront the chilling cost of their mission. The video messages from Earth now span decades, showing children grown into adults, their faces marked by the years the astronauts never lived. The science becomes a backdrop for a profound exploration of sacrifice and the heartbreak of a shared life interrupted by the inflexible laws of physics. On the other end of the cinematic spectrum lies a film like Primer, a low-budget puzzle that treats time travel with meticulous, almost claustrophobic realism. There are no flashing starships or black holes here, just 2 engineers in a garage who accidentally build a box that allows for limited time loops. The film delves into the intricate cause and effect paradoxes that such a device would create, but its true power lies in the psychological fallout. The relentless logic of their situation erodes their friendship, breeding paranoia and moral compromise as they attempt to manipulate their own past for personal gain. The awe of cosmic relativity is replaced by a creeping dread, a stark reminder that controlling time does not mean controlling human nature. These narratives do more than just borrow a scientific concept. They use the bending of time as a powerful metaphor for our own relationship with mortality and memory. They ask us what we would sacrifice for more time and what we might lose in the process. By grounding the universe's grandest mechanics in intimate human struggles, they transform Einstein's equations into a language of emotion, making the relative nature of time feel not just real but deeply personal. Our own conscious experience feels like the only real thing, a steadily advancing now that everyone shares, but relativity shatters this comforting illusion. There is no universal present, no single clock that ticks for all of us. This forces a deeply unsettling question. What is real if your now and my now are not the same? The theory suggests a radical answer, one that physicists call the block universe. In this view, the cosmos is not a story unfolding moment by moment. It is a static, 4-dimensional block where past, present, and future all exist simultaneously, laid out in a fixed structure. Your birth, your reading of these words, and every future event are all already there, permanent fixtures in the grand geometry of spacetime. Our journey through life feels like a moving spotlight of consciousness, illuminating one slice of this eternal block at a time, but the block itself does not change. It simply is. This perspective can feel cold and disorienting. It seems to reduce our lives to a pre-recorded film, where we are merely replaying a script that was always written. If every decision you will ever make is already encoded in the fabric of the cosmos, then what becomes of free will? Are our choices genuine, or are we just following tracks laid down at the beginning of time? This question has haunted both physicists and philosophers for more than a century with no easy resolution, yet perhaps the block universe is not a prison. It might be the ultimate expression of a consistent and lawful cosmos, a reality where every moment holds its own unique and valid perspective. The flow of time may be the deepest illusion of all, a beautiful and necessary trick of consciousness that allows us to experience the story of our own existence. The reality of time's flexibility was proven not in a thought experiment, but with suitcases and airline tickets. In 1971, physicists Joseph Hafele and Richard Keating performed a landmark test. They loaded several incredibly precise atomic clocks onto commercial jetliners and flew them around the world, eastward and then westward. Upon their return, they compared these well-traveled clocks to others that had remained securely on the ground. The results were undeniable. The clocks that had flown were out of sync, showing a measurable time difference. The eastward flying clocks, moving with the Earth's rotation, had lost a few billionths of a second due to their higher speed. The westward flying clocks, moving against the rotation, had gained a tiny amount. This was the combined signature of both relativistic effects at play, the slowing from velocity and the subtle speeding up from experiencing weaker gravity at high altitude. The numbers matched Einstein's predictions with stunning accuracy. Today, the evidence is even more profound. The latest optical lattice clocks use strontium atoms and are so exquisitely sensitive they can detect the warping of time across the height of a single stair step. A clock placed just a few centimeters higher on a shelf will tick imperceptibly faster than its counterpart on the floor because it sits in a minutely weaker gravitational field. These are not theoretical curiosities. They are direct, repeatable measurements from our most advanced instruments. The conclusion is inescapable. Time is not a rigid backdrop. It is a dynamic, personal experience, its rhythm dictated entirely by your local conditions of motion and gravity. This is a fundamental property of our universe, verified beyond any doubt by the relentless tick of technology itself. Hidden within the cosmic shadows, dark matter and dark energy pull the strings of time itself. You cannot see these mysterious components, but their gravitational influence is woven into the very fabric of the cosmos, shaping how time flows on the grandest scales. Take dark matter, an invisible substance that far outweighs all the stars and galaxies we can observe. It does not emit or absorb light, yet it possesses mass, and that mass creates a gravitational pull. This pull shapes immense halos around galaxies, vast, unseen structures that warp the spacetime within entire clusters. When light from a distant quasar passes through one of these clusters, its path is bent by this combined gravity of visible stars and invisible dark matter. This gravitational lensing is a direct map of the warped spacetime, and wherever spacetime is warped, time is dilated. The clocks within a galaxy cluster, governed by this deep, dark gravitational well, tick more slowly than clocks in the empty voids of space. Dark energy presents an even more profound puzzle. It is the name we give to whatever is causing the expansion of the universe to accelerate. This acceleration stretches the very fabric of space, and that stretching imprints itself on the light from exploding stars in the distant universe. When astronomers measure these supernovae, they find them fainter than expected, their light stretched and diluted by the relentless expansion. This cosmological redshift is a form of time dilation for the entire cosmos. The frantic flash of a supernova, which might have lasted weeks in its own local time frame, appears to us as a slow, drawn-out event over many months, its rhythm stretched by the expanding space it traverses. While the true nature of dark matter and dark energy remains one of science's greatest mysteries, their gravitational effects are undeniable. They are the master architects of the large-scale universe, sculpting not only where galaxies are born but also how time itself ebbs and flows across billions of light years. To truly complete our map of cosmic time, we must first learn to see in the dark. Deep underground, spanning the border between Switzerland and France, the world's most powerful microscope operates in a chilled vacuum. The Large Hadron Collider is a 27-kilometer ring where subatomic particles race in opposite directions. scientists accelerate these tiny specks of matter to velocities within a hair's breadth of light's ultimate speed. At these extreme energies, the particles behave in ways that defy their nature, and the key to this transformation is the stretching of time itself. Consider the muon, a heavier, unstable cousin of the electron. Created in cosmic ray collisions high in our atmosphere, a muon at rest would decay into other particles in just over 2/millionths of a second. According to the simple logic of its own internal clock, it should barely travel 600 meters before vanishing. Yet we detect these same muons at the Earth's surface after a journey of many kilometers through the atmosphere. How is this possible? From our perspective on the ground, the muon's incredible velocity, bestowed upon it by the cosmic collision, causes its internal clock to tick far slower. What is a fleeting 2 microseconds in the muon's own time frame becomes a much longer span from our point of view, granting it enough time to reach the surface. Inside particle accelerators, physicists exploit this same principle with breathtaking precision. They create beams of unstable particles and push them to over 99.99% of the speed of light. At these velocities, the relativistic stretching of time is immense. A particle that should live for only a nanosecond in a resting state survives for what seems like an eternity in the laboratory frame, allowing it to travel the length of the detector and leave a clear, readable signature in the surrounding sensors. This is not a theoretical prediction. It is an engineering requirement. Without the profound dilation of time predicted by special relativity, these fleeting particles would decay almost instantly after their creation, vanishing long before any measurement could be made. The entire endeavor of high-energy physics, our search for the fundamental building blocks of all matter, hinges on this silent, continuous proof that time is relative. Every new particle discovered, from the elusive Higgs boson to potential signs of dark matter, is found because we have learned to navigate a realm where the clocks of the tiny run at a different pace than our own. The silent tremors of colliding black holes are about to be heard in a whole new register. A new era of cosmic listening is dawning with observatories like the Laser Interferometer Space Antenna, or LISA. This ambitious mission will not be built on any mountaintop, but will instead consist of 3 spacecraft flying in a perfect triangular formation, millions of kilometers apart, trailing through the vacuum of space. This colossal instrument will tune into the low-frequency gravitational wave universe, a register currently hidden from our ground-based detectors. It will hear the slow, majestic dance of supermassive black holes, millions of times heavier than our Sun, as they spiral together at the hearts of distant galaxies. These waves will carry a pristine signal, untainted by Earth's seismic noise, allowing us to probe the dynamics of spacetime itself with a fidelity we can scarcely imagine. We will not just detect these events, we will essentially watch them unfold, mapping the geometry of the warped spacetime around them and witnessing the final, violent merger that creates a new cosmic giant. How exactly does spacetime ripple and settle in the aftermath of such an unimaginable collision? LISA will provide the answer. Meanwhile, our vision is also sharpening. The Event Horizon Telescope, the global network that gave us the first ghostly image of a black hole's shadow, is not finished. It is adding more telescopes to its array, creating an even sharper virtual eye. Its new target is the immediate environment just outside the event horizon of the black hole at the center of our own Milky Way, Sagittarius, a star. By watching the frenetic dance of superheated gas in this region, astronomers can test the predictions of general relativity with brutal precision. Does the shape of the shadow match what Einstein's equations demand, or will we see a subtle deviation, a tiny crack in the foundation that points toward new physics? The extreme gravity here is the ultimate laboratory, a place where our current understanding is pushed to its absolute limit. To peer even deeper into the cosmic past, the James Webb Space Telescope turns the universe itself into a lens. It uses the immense gravity of foreground galaxy clusters to magnify the light of the most ancient galaxies behind them. This powerful technique, gravitational lensing, does more than just show us faint objects. It allows us to test how the fabric of spacetime has evolved over billions of years. By analyzing these distorted cosmic mirages, we can measure the cumulative effect of dark matter and dark energy on the expansion history of the universe, a history written in the bent paths of light. Each of these next-generation tools is a key designed to unlock a different door in the mansion of relativity. Together, they will scrutinize Einstein's legacy with a combined precision that was once the realm of pure fantasy. They may confirm his vision to a stunning degree, or they may finally reveal the subtle fingerprints of a deeper, more complete theory waiting just beyond our current grasp. The ultimate destiny of all time and space is written in the language of relativity. Our cosmos is not static, it is a dynamic story unfolding, and its final chapter will be determined by a delicate cosmic tug-of-war. On one side, the total matter and energy content of the universe pulls through gravity, working to slow the expansion and potentially pull everything back together. On the other side, the mysterious force we call dark energy pushes, accelerating the expansion and driving the galaxies apart. General relativity provides the very framework for this epic struggle, defining how the geometry of spacetime itself responds to what fills it. The rate at which the universe expands is not constant. It is a changing signal that holds the key to our fate. This expansion rate directly influences the cosmological time dilation we observe in distant supernovae, stretching out their light and making their explosions appear to unfold in slow motion from our vantage point. By meticulously measuring how this expansion has accelerated or decelerated over billions of years, cosmologists can infer the true nature of dark energy. Is its push constant, or does it grow stronger over time? The answer dictates one of three possible endings. In one scenario, gravity eventually wins, reversing the expansion in a cataclysmic big crunch where the entire universe collapses back into a singularity. In another, the expansion continues forever, with galaxies receding until each star burns out in isolated darkness. The most dramatic possibility is the Big Rip, where dark energy becomes so dominant that it overwhelms all forces, tearing apart galaxies, then solar systems, and finally ripping atoms themselves to shreds at a single moment. These are not just abstract fates. They represent the final expression of time's relativity on the grandest possible scale. The local time warps around planets and black holes are mere eddies in this vast temporal river, a river whose current is set by the deepest architecture of reality. Our quest to understand when time slows down ultimately leads us here, to the beginning and the end of everything, framed by the enduring power of Einstein's vision. A stretched rubber sheet offers a powerful way to visualize the invisible. Picture spacetime not as an empty stage, but as this flexible, fabric-like surface. When you place a heavy object like a bowling ball in the center, representing a star, it creates a deep, smooth depression in the sheet. This curvature is gravity. Now take a marble and set it rolling near the bowling ball. Instead of flying off in a straight line, the marble naturally follows the curve of the depression, tracing an orbital path around the central mass. This simple model shows how planets are not pulled by a mysterious force, but simply follow the contours of warped space. But the analogy goes further, revealing the intimate link between space and time. Imagine rolling a second marble very quickly across the sheet, far from the bowling ball. Its path will still bend slightly as it crosses the gently curved surface, but something else happens from your perspective as a stationary observer. That fast-moving marble's journey across the sheet appears to take just a little bit longer than if the sheet were perfectly flat. This is the analog of time dilation. The marble's high speed through the warped geometry means its own clock ticks slower relative to yours. The model is not perfect, of course. A real rubber sheet relies on Earth's gravity to create the dip, while spacetime itself is the source of the curvature. Yet this tangible scene helps make the abstract concrete. It illustrates how mass tells spacetime how to curve, and how that curved spacetime then tells everything within it, from planets to light beams, how to move and how to experience the flow of time. This elegant interplay is the heart of Einstein's universe, transforming the cosmos from a cold void into a dynamic, geometric landscape where every object writes its own story in the fabric of reality. This intellectual revolution tore through the foundations of human culture. For centuries, Isaac Newton's clockwork universe offered a comforting predictability, a realm of absolute space and time where every effect had a clear cause. Einstein's relativity replaced this with a cosmos of probability and perspective, a shift that resonated deeply with artists and thinkers who were already questioning the very nature of reality. You can see this transformation vividly in the fractured planes of Cubist painting. Pablo Picasso and Georges Braque did not simply paint an object from one angle. They presented multiple viewpoints simultaneously, showing the front, side, and back all at once. This was a visual declaration that there is no single, privileged way of seeing, a direct parallel to relativity's dismissal of a privileged frame of reference. The canvas itself became a block universe where every perspective coexisted. This new world view also instilled a profound humility. It demonstrated that our instincts, shaped by the slow speeds and weak gravity of Earth, are not universal laws. The universe operates on rules that are hidden from our immediate senses, yet accessible to human reason and creativity. The word relative itself escaped the physics lecture hall and entered everyday language, becoming a shorthand for the idea that truth can depend on context. This was not a descent into mere subjectivity, but an elevation of understanding. It showed that our perception is part of the system we are trying to measure. The theory became a powerful metaphor in literature and philosophy, challenging rigid dogmas and encouraging a more nuanced view of truth. It was a stunning affirmation that the human mind could grasp realities that are utterly alien to our daily lives, revealing a cosmos far stranger and more wonderful than anyone had previously dared to believe. Such profound ideas inevitably give rise to stubborn myths. A frequent misunderstanding is that time dilation is merely an illusion, a trick of perception or a flaw in our measurements. This could not be further from the truth. The slowing of time is a real, physical phenomenon, as tangible as the force of gravity, confirmed by atomic clocks on jets, the precise timing of orbiting satellites, and the decay of particles in giant accelerators. The universe itself operates on this principle. Another seductive but flawed idea is the dream of practical immortality through near-light speed travel. The math does show that a traveler moving at a tremendous fraction of light speed would age far less than everyone on Earth. Yet your own personal experience of time during such a journey would feel completely normal. Second by second, minute by minute, your life would proceed at its usual pace. You would not feel a magical suspension of your own existence. Furthermore, the sheer energy required to accelerate a spacecraft to such velocities is so astronomically vast that it places this concept firmly in the realm of theoretical possibility, far from any practical application we can foresee. Perhaps the most crucial clarification involves causality itself. Some wonder if bending time could allow an effect to happen before its cause, creating a logical paradox. The universe, however, has a fundamental safeguard. The universal speed limit of light ensures that information cannot travel fast enough to create such a reversal in any valid reference frame. While different observers may disagree on the timing of distant events, the fundamental sequence of cause and effect remains sacred and unbroken. The order of the cosmos is preserved. Clearing away these misconceptions is not just about scientific accuracy. It allows us to appreciate the true, elegant strangeness of relativity, a theory that describes a universe both wonderfully bizarre and rigorously logical. Our own mind possesses a clock that defies every cosmic rule. Physics gives us the precise, mathematical warping of space-time, yet our personal experience of time is a fluid and often unreliable impression. An hour spent waiting in a dull, silent room can feel like an eternity, while that same hour in the company of good friends can vanish in what seems like a moment. This is the domain of psychological time, a phenomenon governed not by gravity or velocity, but by the intricate workings of our own brain. It is a function of where we direct our attention, how our emotions are stirred, and the way we lay down new memories. During periods of high engagement and novelty, our brain is busy processing a rich stream of information, creating dense memory formations. When we look back, that packed timeline feels long and full. In contrast, monotonous routines require little new processing, resulting in sparse, compressed memories that give the illusion of time having flown by. This subjective river of time flows independently from the objective ticking of any atomic clock. An astronaut on the International Space Station, with their clock minutely slowed by both speed and weaker gravity, could still feel a day drag on if their work was tedious, or rush by if they were captivated by the view of Earth. This stark dichotomy reveals a profound separation between the external, measured universe and our internal, conscious perception of it. We are living in two realities at once, one ruled by the immutable laws of physics, and the other crafted by the unique architecture of our own mind. What would it be like then to truly inhabit a place where physics dramatically alters the clock? If a human consciousness were placed near a neutron star, where gravity slows time to a crawl relative to the outside universe, how would the mind reconcile the objective slowing with its own internal rhythm? Would a minute of boredom in that immense gravity feel just as long as a minute of boredom on Earth? The blend of neuroscience and physics suggests that our conscious experience might remain anchored to our personal, biological processes, even as the cosmos warps time around us. This reveals time not as a single entity, but as a multifaceted jewel, with one face cut by the laws of nature and another polished by the lens of our own awareness. Our journey through the cosmos reveals a universe where time is not a rigid backdrop but a dynamic participant in the cosmic dance, its rhythm dictated entirely by gravity and velocity. This is not a theoretical abstraction. It is the silent, continuous reality that governs everything, from the precise ticking of the GPS satellites guiding your drive to the infinite stretch of a moment at a black hole's edge. These relativity effects are not anomalies. They are a fundamental and deeply confirmed part of the fabric of our existence. This understanding has rippled through human civilization, revolutionizing the technology we build, the philosophy we contemplate, and our very sense of place within the grand scheme. The next time you glance at a clock, pause for a moment. That device is measuring a local, personal time, a rhythm unique to your specific position in the gravitational landscape and your state of motion. Across the vast expanse of space, countless other clocks are ticking at entirely different rates, from the frenetic pulse of a distant quasar to the near-frozen heartbeat of a neutron star. Yet all of these divergent timelines are woven together into a single, magnificent fabric called spacetime. Let this expanded perspective be your invitation. Look up at the stars on a clear night, not just as distant lights, but as anchors in a curving, dynamic universe. Each point of light exists in its own now, its own time frame, all part of a cosmic story still being written. What other profound mysteries are waiting just beyond our current grasp for a curious mind to uncover?